Hello students, welcome back to Chemistry Online class. Today we are considering the trends in the periodic table. Now, looking at the periodic tables which are arranged based on the group and periods. Now there are 8 groups and there are 7 periods. The groups are arranged vertically according to their valence electron, while the periods are arranged based on the number of shells. So members of group period 1, they are hydrogen and helium because they have 1 and 2 electrons in their shell. So that's occupy the first shell. We can only take a maximum of 2 electrons. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorinium takes 2 shells. All the electrons are filling 2 shells because they have from 3 to 10 electrons in their orbitals. Now, let's consider group 1 element. All group 1 elements has 1 valence electron. You know, groups are arranged vertically. And each members of this group they are representatives of different periods. For instance, hydrogen is in group 1 and is in period 1 because it has 1 shell. Lithium is in group 1 but in period 2 because it has 2 shells, because the atomic number is 3. Sodium is in group 1 but period 3 because it has electrons of 11. Atomic number is 11. That's 2, 8, and 1. And then lastly, potassium is in group 1 but period 4 because it has 2, 8, 8, and 1, 4 shells. And you can see that down like that, as you go down the group, their sizes increases due to increase in the number of shells. So this is one of the trends, the atomic size or atomic radius. If you look at the radius of a circle, it starts from the center to one side. So if you are talking about atomic radii now, we talk about the distance between the nucleus of 2 close atoms, atomic nuclei of an element. So we can see this is the center of another atom. This is the center of one atom here. This is the center of another atom. This is the radius of one atom. This is the radius of another. So if we trace this like this, we get the atomic size of that element. And so we can see here that the atomic sizes increases down the group due to increase in the number of shells. So what do we now talk about? How do we get their atomic sizes across the period? If you look at helium, neon, argon, the same thing happens. If you look at boron and aluminium, boron has an atomic number of 5, 2, and 3. And aluminium is 13, 2, 8, 3. What is common to them? 3 valence electrons. That's why they are in group 3 in the periodic table. But if you go down the group, you will notice that their sizes increases down the group. The same is applicable to all groups. Now, but for periods, how do we classify elements into periods? We use their number of shells. So going across the period, we will say that we have the same shells. Now, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorinium all have 2 shells. But there's something happening there. We can see here that in lithium, atomic number is just 2. And electrons is, the valence electron is 1. For beryllium, electron here, they are just 4. So the same electron is added to the, different electrons are added to the same shell as we move across the period. We see that atomic number is increasing by 1. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen. Atomic number is increasing by 1. And electrons are added to the same shell. Now, nitrogen is still the same shell. That's 5 valence electron, 2, 1, 1, 1. And like that, we can see that the number of shells are not increasing, but something is happening. What's happening here? We see that as the atomic number is increasing by 1 across the period, atomic number is the number of proton in the nucleus of the atom of an element. And looking at the structure of an atom, we have the nucleus that has proton and neutron, then the shells has electron. Proton is positively charged, while the shells which contains the electrons or the orbitals are electrons there are negatively charged. There's an attraction between the positive and the negative charges. So we can see that if atomic number increases, proton power will increase. So as electrons are being added to the same shell, as atomic number is increasing across the period from boron to carbon to nitrogen is increasing by 1. We see that the number of proton is increasing, which is positive charge. And this positive charge is in the nucleus of each element. Now, all these represent electrons and they are negative. Now, So we can see that as the proton power is increasing and electrons are added to the same shell, the shell numbers are not increasing, we will see that there will be a stronger increase in the attraction of electrons to the proton, which is inside the nucleus. So because the proton power is increasing due to an increase in atomic number, because atomic number is the number of proton. So because atomic number is increasing by 1, the proton power is increasing by 1. And so there's an attraction of electron, a stronger attraction of electron to itself. So in that case, we can summarize that atomic sizes decreases across the period, but increases down the group due to increase in the number of shells down the group. But across the period is decreasing, though it's not visible, but it's reducing in size because of the greater attraction of the proton nuclear charge, which is in the nucleus, by drawing electron to itself. Now, let's also look at the electropositivity, electronegativity down the group. That has been treated in my first video on periodic table. Electropositivity is increasing down the group because the tendency to lose electron is increasing. Electropositivity is the ability to lose electron. When elements lose electron, they become positively charged. Now let's look at group 1 element. They are called alkali metals because they form alkalis when they react with water. Why are they alkali metals? And they are the strongest electropositive elements, the most electropositive in the periodic table. Why? Number 1, they are in group 1 because they have 1 valence electron. Number 2, they are alkali metals because they react with water to form alkali, which are strong bases. A very good example is potassium hydroxide and sodium hydroxide. After reacting with water, sodium reacts with water to form sodium hydroxide and hydrogen gas. Potassium reacts with water to form potassium hydroxide and hydrogen gas. Now, why is it that electropositivity is increasing down the group? We can see that all of them have 1 valence electron in their orbitals. Hydrogen has 1 valence electron, lithium has 1 valence electron, sodium has 1 valence electron. What is valence electron? Electron at the outermost shell. And the potassium also has 1 valence electron because it's 19. 1 valence electron. But why is it easier to lose electron for potassium? Because ability to lose electron is electropositivity. It is easier because this last electron is far away from the proton nuclear charge. That's proton that is positive, which is in the center of the nucleus, always drawing the electrons which are negative on the shells to themselves. And because this shell, the shell number of potassium is 4, 2, 8, 8, 1, compared to sodium that is just 3. So the valence electron of sodium is still closer to the proton power, which is positive in the nucleus. While that of potassium is far away, the electron is far away from the proton nuclear charge. Look at the structure vividly. This is like the valence electron, the last one. Electrons are found here. And there's a proton nuclear charge, which is 19, because atomic number of potassium here is 19. So atomic number is the number of protons. So proton is also 19. But because the proton power is increasing, it's drawing all the shells to itself. Is it not supposed to be stronger? Is ability to lose electrons supposed to be difficult? Because it's supposed to be reduced rather. Because this proton power is 19, drawing all the shells and the electrons to themselves, because potassium has more proton power because the atomic number is the greatest, 19. That is how it's supposed to be. But this factor will not work because of the distance. The effect of distance of this valence electron is far away from the proton. Even though the proton has power, is 19, is higher than the proton power of potassium and sodium, which is 11 atomic number. And lithium is 3 because the atomic number is 3, the proton is 3. Atomic number is 1, proton is 1. Atomic number is 11, proton power, which is in the nucleus, is 11. And potassium is 19 because atomic number is 19. The proton power is also 19. And proton is positive. It's always drawing all the electrons to themselves. But this valence electron, the last one for potassium, will be lost easily. The ability to lose will be easier because it is far away from the proton nuclear charge. It's just like somebody who has you have 10 sweets, you can easily give out 1 compared to somebody that has 7 giving out 1, or someone that has 3 giving out 1. It's difficult for someone with 3 to give out 1 electron instead of compared to somebody with 10 or 7 to give out 1. So the ability to lose electron is increasing down the group because of the distance of that valence electron that will be lost from the proton nuclear charges that's always pulling the electron to itself. So it's easier losing as you go down the group. And because it's easier losing as you go down the group, the energy required to remove the valence electron, that valence electron from an atom to form, from a gaseous atom to form a gaseous ion, is electropositivity. That ionization energy required will be reduced because it's easy removing the valence electron as you go down the group. So definitely ionization energy will reduce. But across the period, sodium, magnesium, aluminum, silicon, phosphorus, you can see that if you draw their shells, electrons are drawing nigh to stability, close to stability. Sodium, for instance, here, sodium has atomic number of 11. So we have 2, 8, 1. Magnesium, 2, 8, 2. Aluminum, 2, 8, and 3. Now, electrons are drawing close to stability here. And because the proton power is increasing, atomic number is increasing from sodium to magnesium to aluminum by 1. So definitely atomic number is the proton power or number of proton in the nucleus of the atom of an element. Because this atomic number is increasing and electrons are added to the same shell, the distance is not increasing because the shell numbers are not increasing. And the proton power is increasing by 1 as you go across the period. We can see here that the ability to draw electron, because the proton is positive, always attracting electrons to itself, is increasing. It's drawing the electrons to themselves and to itself. So it will be difficult to lose electron as you move across the period because of the increase in the atomic number and decrease in the number of shell. So the tendency to lose or give out electron will be lower, and so that is, but the tendency to gain will be increasing, because when we get to a point here in sulfur, we gain 2, chlorine we gain 1 because it has 7 valence electrons. It's easier gaining in that case than losing out. Chlorine is 17, 2, 8, 7. It will gain 1 more to make the last shell 8. So in that case, the tendency to gain electron is increasing, it's just increasing. So the non-metallic property, which is electronegative property, is increasing as we move across the period. And so in that case, ionization energy is increasing. It will be difficult to remove the valence electron now. So it requires more energy to remove the valence electron, and that is ionization. So ionization energy is increasing across the period and decreasing down the group. Now, the electron affinity is another factor, which is the energy released anytime there's a gain of electron. So because electrons, the ability to gain electron is increasing, or the tendency to gain electron is increasing, we can see that the electron affinity too will be greater. The higher the electronegativity, the higher the gain of electron, the greater the electron affinity. That is, for instance, now, carbon here is 6. We have 2 and 4. Now, nitrogen is 7, 2 and 5. Oxygen is 2, 8, 2 and 6. And how do we draw the 6? This one needs 2 more to complete its shells. This one needs 3 more to complete its shell. Fluorine is 9, 2 and 7. It needs 1 more. So we can see here that it's easier to gain as we move across the period because electrons are drawing nigh to stability. So because of that, the energy released anytime an electron is gained is electron affinity, which is also increasing across the period and is reducing down the group because there's no gain of electron. Rather, there is a loss of electron down the group. The loss of electron is increasing. Looking at the halogen group now, the most electropositive is fluorine. Electronegativity across the period is increasing because the electron is drawing nigh to stability, which is the non-metallic property. And electronegativity down the group is reducing because the tendency to lose electron is increasing because valence electron is getting far away from the proton nuclear charge. For chlorine now is 2, 8, 7, unlike fluorine that is 2 and 7. So the last shell, we take 7 for chlorine, is far away, and the electrons, they are far away, they can be lost, compared to fluorine, which has 2 and 7, and the electrons are closer. So electronegativity down the group is what? Is reducing. The tendency to lose is increasing, which is electropositivity. So thank you. Watch out for more of my videos. Don't forget to like, subscribe, and also share my videos. Thank you very much.